Okay, let's have our first discussion of the periodic table. As you may know, as elements were being discovered and characterized, people began to collect them into arrangements. And one of these arrangements, which was particularly powerful, was that of Mendeleev. Now, Mendeleev originally arranged atoms in order of increasing atomic mass because no one knew about atomic numbers. But we've since learned that atomic numbers are a more appropriate way to arrange the atoms. For one thing, as you know, that it's the atomic number that determines what the atom is. You can have different atoms with the same atomic number and different atomic masses. Those are, of course, called isotopes. So instead, we arrange the atoms in the periodic table in order of increasing atomic number. And like Mendeleev, we see a pattern. So after hydrogen comes the first noble gas or unreactive gas called helium. We like to fill our balloons with helium. Helium is completely unreactive, and interestingly enough, its average speed is fast enough that once helium gets released into the atmosphere, it goes right into outer space. It has an average speed higher than the escape velocity from the Earth. Then we come to lithium, which is a very active metal. You've probably heard a lot about lithium these days in terms of batteries, and one of the reasons lithium is so popular is because it's so light. Next to lithium is beryllium. Beryllium is a more brittle, also reactive metal. And as we move across from beryllium to fluorine, from atomic number 4 to atomic number 9, the characteristics of the elements change pretty systematically until at 9 we come to fluorine, and fluorine is a reactive gas. As a matter of fact, diatomic at room temperature. And then after fluorine comes neon, and neon looks for all the world like helium. It doesn't react with anything. It is a very stable gas. It's heavier, so we don't lose it to outer space. But still, it has no reactivity at all. After helium, interestingly enough, the pattern begins to repeat itself. So you've got sodium, which has very similar properties to lithium. I'll show you that in a minute. Magnesium, likewise, has very similar properties to beryllium. And if you keep listing the elements across from 12 to 17, such that 17 falls right beneath fluorine at 9, we find that chlorine and fluorine have very similar chemical properties. They're both extremely reactive diatomic gases. And the next one up, argon, is our third noble gas. With potassium, the pattern repeats again. It's not quite 288, but the pattern is unmistakable. So the periodic table is, in fact, a document which takes advantage of these properties such that it lists the elements in order of increasing atomic number, but it puts elements with similar chemical properties underneath one another in the column. So the row, as you go across the periodic table, represents elements with increasing atomic number, but each column has elements which have similar chemical properties. So here's a periodic table, the kind that we'll be using, except in our case will include the atomic mass, the average atomic mass. This periodic table only has atomic numbers. But if we look, the first row in the periodic table are known as the alkali metals. Hydrogen is an exception to this. You'll see it here, and often it's also placed in row 7A, but it has special properties we'll talk about in a little while. On the other hand, all the other elements in column 1, which are known as the alkali metals, and this you need to remember, the names of some of the columns I'm about to list. So the first group are the alkali metals. The second group, the alkaline earth metals. Again, these are all metals that we find in nature, though almost all of them are found not as the metal, but as the metal cation. Next to the group 2 metals are the transition metals, and there are 30 of them, depending on how you count. This last row, starting with lawrencium, are unstable. As I mentioned already, everything above bismuth in the periodic table is radioactive, and these elements are so radioactive that they've been made in the laboratory and only stuck around for fractions of a second. So the important transition metals are the 30 that are listed in the 3 by 10 column you see here. In addition, then, we have the halogens, fluorine, chlorine, bromine, iodine, and actinium, known as the halogens, and finally the noble gases. So those columns, the alkali metals, the alkaline earth metals, the transition metals, the halogens, and the noble gases, you need to know the names of those columns as I've just indicated they are. In addition, it's important to know which elements exist in nature as diatomics. So nitrogen, oxygen, and all the halogens are diatomic in their elemental form in nature. Okay, to give you an illustration of what I mean by similar chemical properties, let's look at the reaction of each of these alkali metals with water. So we start with lithium. Notice, and I'll do that again, notice that there's smoke that comes off the reaction, that the lithium in fact floats on water as it reacts with the water. And this is the equation that describes the reaction of lithium with water to form the lithium cation, lithium plus 1, and 2 hydroxides and hydrogen. So the gas that's escaping as this reaction takes place is hydrogen gas, and the solution is also becoming basic. We'll talk about that in some detail a little bit later on because of the production of hydroxide. Let's now look at sodium. Again, you see that it floats and produces a gas, the gas being hydrogen again. And you see that the equation describing the reaction of sodium with water is very similar to the one describing the reaction of lithium with water. You may know that more than one person has been seriously injured by reacting sodium directly with water because that reaction can be explosive. All right, if we go to potassium, we see a slightly more violent reaction. Notice that this time we actually have a flame. The reaction is the same one as before, but this time it appears that there is some ignition of the hydrogen that's being produced. If we look at rubidium, you can see already that the experimenter is wearing gloves. And you see that the reaction is much more violent than even the reaction of potassium with water. And finally, we get to cesium. And this reaction, you'll see, is the most violent of all. So while the rate at which these reactions occur, and therefore the explosiveness with which they occur, may vary as you go down the column, the reaction they undergo is always the same. It always forms the +1 cation, it always produces hydroxide, and it produces hydrogen gas. That's what I mean when I say that elements in the same column of the periodic table have similar chemical properties.